Yeah, I'll react to that, sure. This stuff is so fascinating. Hey guys, original link top of the description. Engineer guy, preemptive like, the steam turbine. Let's learn.
To understand the relationship between engineering and science, I share the story of how an engineer created a revolutionary engine by taming the extraordinary power of steam. We can hear the source of that power with a tea kettle. The boiling water turns to steam. The steam's volume is much greater than the liquid water, and so as it expands, it exits the spout with enough energy to create that characteristic whistle. The amount of expansion is stunning. 1 cup of liquid water, which I'll represent as this tiny dot, when boiled, expands into 1,600 cups of steam. That dramatic change of volume, that expansion, exerts a force that engineers tapped in.
Wait, but what does 1 cup of steam look like? You know? Because you can keep pushing steam in to a cup and compress it.
Into in the early 18th change of volume, that expansion.
So I'd assume a cup of steam would be steam filling up a cup where it has no pressure to escape that cup.
Exerts 100 cups of steam. That dramatic change of volume, that expansion, exerts a force that engineers tapped into in the early 18th century to drive reciprocating steam engines. With this demonstration engine, we can see inside and watch the inner mechanism. The engine is driven by air right now, but we can trace the path of the steam. High-pressure steam enters here. It follows this channel to the piston, where as the steam expands, it pushes the piston to the right. Let's watch that again, but this time more slowly, and notice what happens here. As the piston reaches the end of its travel rightward, this section, called a D valve, slides in the opposite direction and reroutes the steam. Steam now travels to the right side of the piston, while the steam on the left side, the spent steam, can exit through this route. The fresh steam drives the piston back to the left, and the
Wait, couldn't you have... I'm obviously wrong, but why would you need it to exhaust? Couldn't you just have it keep going back and forth?
process repeats. This motion, called reciprocating, isn't very useful. We want rotation this route. The fresh steam drives the piston back to the left, and the process repeats. This motion, called reciprocating, isn't very useful. We want rotative motion. To translate reciprocating motion to circular motion, this engine uses this set of levers.
So the steam comes in here. These two are blocked, so it has to go in here, which pushes this here, which pushes this back, which pushes this back, and then uncovers this, and it can go in, and then this pushes more steam in, and you repeat. Okay, and then
In that way,
and then you're putting something on here.
reciprocating engines drove in the 19th century motion. To translate reciprocating motion to circular motion, this engine uses this set of levers. In that way, reciprocating engines drove in the 19th century the wheels of steam-powered locomotives. If I overlay our demonstrator engine, you can see the location of the piston cylinder and the levers that convert the reciprocating motion to rotational motion. Well, the reciprocating steam engine revolutionized the world. It wasted much of the steam's energy. Once the steam has expanded to about 16 times its original volume, it lacks the oomph, the force to overcome the friction of the heavy piston within the walls of the cylinder, and friction in the arms that convert
WD-40?
reciprocating motion into circular motion chew up some of the steam's energy.
Okay, so this still kind of confuses me, how you're turning it into circular rotation. So this goes...
convert reciprocating motion into circular motion, chew up some of the steam's energy. But in the late 19th century, a novel steam engine appeared that used the energy from an expansion of an astonishing 479 times a cup of water's volume. That novel engine was perfected by this man, Charles Parsons. While a huge leap forward, no one would buy his engine, especially the British Navy and the large cruise line companies like White Star and Cunard. And so in frustration, he built this ship to convince everyone of the superiority of his engine. This T-card, a trading card package with T's sold in the 1950s and 60s, features the Turbine, as Parsons named his small ship. To attract attention, he crashed a naval display honoring Queen Victoria's Diamond Jubilee in 1897. Throughout these ships, you see the Turbine here, Parsons buzzed around outpacing the Navy's fastest patrol boats. Parsons' stunt worked. Within 10 years, his new steam engine dominated marine propulsion. Parsons' engine eliminated the need for this piston and cylinder and these levers used to create rotary motion. He did this by fusing two ways of using steam to rotate a shaft. The first is this device, called an eolipile, designed by Hero of Alexandria in about 130 BC. It has a chamber and three nozzles.
Right, and the steam comes out of here and keeps spinning.
The chamber is filled with water, then heated. At first, water shoots out, but when the water in the chamber expands to steam, it blasts through the nozzles and spins the device. The key idea here is that a shaft is being turned directly by the steam. No need for pistons, cylinders, and levers. This device, while delightful, doesn't have enough power to do much useful. To generate enough torque to drive something like an engine shaft, the steam pressure must be increased in the chamber, but then the steam would blast from the nozzles at a tremendous 1,200 miles per hour, many times faster than the most powerful hurricane winds. At such a speed, the eolipile would tear itself apart. In fact, I destroyed several of these toy devices. If it spins too fast and is the least bit out of line, it careens off its stand and is usually destroyed. The second method to use steam to directly turn a shaft is shown in this fanciful woodcut from the 17th century. In 1629, an Italian engineer, Giovanni Branca, designed a giant boiler shaped like a human head. From its mouth, a jet of expanding steam struck a paddle wheel, much like a water wheel, which turned gearing that drove two pestles that pounded mortars. When engineers built devices like Branca's, not only did the paddle wheel spin so fast that it blew apart like Hero's eolipile, the high velocity of the expelled steam cut through the metal of the paddle wheel. These uses of steam to rotate a shaft are simple in principle, yet in the century preceding Parsons' successful 1885 design, some 200 patents were filed in the United Kingdom on using steam to rotate a shaft, none of which worked. Parsons succeeded by cleverly combining these two methods. This is a small version of Parsons' solution, although incomplete, as we'll see in a moment. It's a long shaft with bladed wheels. Steam enters here, which spins the wheels, which turns the shaft of course, connected to a ship's propeller or a locomotive's wheels. The action of the steam is like that of Branca's device, in that steam strikes the blades and causes the wheel to rotate. But in addition to this impulse force of the steam, as in Branca's device, Parsons wanted to use the reaction of the eolipile. Recall there that the steam exits the nozzles to rotate the device. To incorporate that action, he placed between every rotating wheel on the shaft a stationary wheel. These wheels are affixed to the casing and not to the rotating shaft. Notice here that as the front wheel rotates, you see the blades of the stationary wheel behind it. To see how this incorporates the action of the eolipile, let's x-ray through one of the stationary wheels so we can see the shape of the blades. The scallop-shaped blades on the spinning and stationary wheels are angled in opposite directions. The steam strikes the first spinning blade, as in Branca's device, it rotates the wheel. The first wheel is further propelled when the exiting steam strikes the immobile blades of the stationary wheel that follows. So the steam exiting that first wheel is like the jets from the Eola pile. Next, the blades of the stationary wheel redirect the steam, which strikes the next wheel, which rotates as in Bronco's device. The steam exits that spinning wheel and pushes against the blades of the stationary wheel. This process repeats throughout the device. Parsons' engine had 30 wheels, half of which were moving.
I still don't really understand the reason for the stationary wheels. I know what they're doing. They're redirecting, but I still don't know why that's needed.
And half of which were stationary. He called this device a turbine. The reason he used 30 wheels was that it avoids the device-destroying speed created by the jets of the Eola pile, or the cutting action of fast-moving steam, as in Bronco's device. Parsons' turbine. He called this device a turbine. The reason he used 30 wheels was that it avoids the device-destroying speed created by the jets of the Eola pile.
So it lessens the force. So do the stationary wheels effectively keep the non-stationary wheels from spinning too fast?
Or the cutting action of fast-moving steam, as in Bronco's device.
Okay, so the cutting action, as in the power of the steam itself. Okay. So instead of the steam being pushed onto a flat surface that will just wear the surface and even cut through it, it's hitting at angles so that the force is redirected constantly instead of just okay.
Device against the blades of the engine. He called this device a turbine. The reason he used 30 wheels was that it avoids the device-destroying speed created by the jets of the Eola pile.
Okay.
Or the cutting action of fast-moving steam, as in Bronco's device. Okay. Parsons' turbine controls the release of the...
So the number of the wheels and the angles, the number of the wheels and the largeness of the shaft, the number of the wheels, prevents it from spinning too fast, and the angles prevent it from the steam just damaging each and one of the wheels.
Steam's energy, and thus the rotational speed of the shaft, because steam expands in small steps a little bit across each wheel. Parsons' turbine controls the release of the steam's energy, and thus the rotational speed of the shaft, because steam expands in small steps a little bit across each wheel. This design is simple in concept, but Parsons described the execution as of almost infinite complexity. Think of what he needed to know or estimate: the number of steps he should use to slowly expand the steam, the speed of rotation caused by the steam's expansion at each step, because he needed every wheel to rotate at the same rate. The device wouldn't work if this wheel and this wheel spun at different rates, because the shaft would be twisted to bits. The steam was expanding as it traveled down the turbine, so he needed to adjust the spacing in the blades to ensure the uniformity of the wheel's rotational speed. In this schematic, they appear to be the same size, but if we look at Parsons' actual turbine, we see the different size bladed wheels as the steam progresses through the turbine. In this turbine, the shaft runs from the bottom of the photograph to the top, and steam enters from here. The bladed wheels are here. Notice the size difference between this section and this section. As the steam moves through the turbine, it expands. To accommodate that expansion, Parsons enlarged the spacing and the diameter of the bladed wheels. This highlights that Parsons faced an astronomical number of dimensions and configurations of wheels and blades and every other design variable in his turbine. What separated Parsons from the thousands of inventors before him was, he said, the data of the physicists. And in that statement is the link between engineering and science. Parsons drew on the data in these 3 volumes. pages. They contain a lifetime of work by the now forgotten French scientist Henry Victor Regnault. The patient and careful Regnault spent nearly 30 years documenting, as reported in these 3,000 pages, the properties of steam. He devised clever gadgets and gauges to measure, at all temperatures and pressures, the energy contained in steam, its volume, the energy required at these temperatures to turn steam into liquid water, and vice versa. From the data tabulated here, Parsons could determine the amount steam expands and its velocity at every wheel in his turbine. That's how he knew how much to increase the blade spacing as the steam traveled down the turbine. For Parsons, scientific knowledge helped rule out what wouldn't work, narrow the possibilities of what does, and shorten the path to a solution. If we return to our definition of the engineering method, solving problems using rules of thumb that cause the best change in a poorly understood situation using available resources, we now can see where science enters. Scientific practice and knowledge offers engineers gold-plated rules of thumb. Rules that work better than those observed from observation or trial and error. Although the turbine was a 19th century invention, Parsons' turbine still enables the daily lives of nearly every human on the globe as its descendants continue to generate the world's electricity with steam power. In the next video, I'll explore a single word from this definition of the engineering method. What exactly does an engineer mean by best? I'm Bill Hammack, the Engineer Guy.
That's a great video. I find this stuff fascinating. I love watching videos like this. Hope everyone's doing well. Would appreciate any comments down below. I was confused a bit during it, and I still don't have 100% grasp on exactly how everything works, but I feel like I'm satisfied with what I learned in the video, so that was fascinating. Hope everyone's doing well. Hope I'll see you guys next time. We'll keep on learning together. Bye, guys.